This is an accompanying video for ICRA 2024 submission of sim to real object pose estimation for random bin picking. In image-based methods, the use of geometric information is often auxiliary, or not used at all, making these methods susceptible to environmental changes. On the other hand, point cloud-based methods leverage geometric information. This makes them robust to photometric influences and occlusions. However, most of these methods are specifically designed for either segmentation or pose estimation. For deep learning training data is essential. However, most of the existing data are monotonous indoor or autonomous driving scenes, so they are not suitable for complex bin picking scenes. Moreover, directly annotating point cloud data is extremely labor-intensive. To address these challenges, we propose the sim to real object pose estimation for random bin picking. This represents a unified framework for learning 6DOF pose estimation for complex bin picking scenes using only CAD file input. The proposed method acquires annotated data through simulation for training, and consists of sequential learning, networks, segmentation, and pose estimation, using the generated data. Here's an introduction to the process of generating data. We take a single CAD file as input, and simulate dropping the object from various positions. Based on the resulting poses of these stacked objects, we generate point cloud data with annotated labels. We then remove the invisible regions. In the segmentation part, we group the 3D UNet features. Subsequently, the query decoder with transformers enables query vectors to learn instance information through feature cross-attention. While this structure is similar to the SPFormer, the pooling layer is what sets them apart. We modified the pooling layer previously based on Superpoint to be more suitable for complex bin picking scenes by incorporating the cluster pooling layer. The network for pose estimation learns the probability that each point lies in the overlapping region and its corresponding position in the other point cloud. An initial pose is computed from the good correspondences. ICP fine-tunes the final pose based on the inferred initial pose. In the ablation study, we observed that performance improved as the number of groups increased due to the complexity of the bin picking scene. Interestingly, when we generated over thousands of groups, Euclidean clustering exhibited both faster computational speed and better performance. We evaluated the segmentation performance of our proposed method through benchmark results. As shown in the figure, our method clearly distinguished objects even in the overlap area. Our algorithm demonstrated higher precision and recall performance compared to the previous methods. Additionally, compared to PPF, our method recognized the poses of approximately twice as many objects. We conducted a robot bin picking experiment using the proposed method. After estimating the object's pose and picking points, we performed a collision check to determine the optimal picking point. This depicts the process of obtaining point cloud data, using the Zivid sensor, estimating the object's pose from it, and subsequently performing robot-based picking. The image in the top right corner illustrates the pose estimation results. The red line represents the final picking point and orientation.